Hi, my name is Connor Wolf, and this is the video abstract for the paper Twirled Perfect Tensor Networks, Computationally Covariant Holographic Tensor Networks, written by Gerbier Aurora, Matthew Hedrick, Albion Lawrence, Martin Sassieta, Brian Swingle, and myself. The motivation for this work starts with the Python's lunch conjecture. This conjecture concerns geometries which have entanglement wedges with multiple quantum extremal surfaces. The region between the quantum extremal surfaces, shown here, is called the Python's lunch. The PLC predicts that the complexity to reconstruct information inside the lunch will be exponential in the area difference between the index 1 surface, shown here, called the bulge, and the non-minimal QES, called the constriction, shown here. This prediction comes from tensor network considerations, where we assume that the Python's lunch can be represented via low-complexity tensor network. Then all of the exponential complexity comes from the post-selection required to contract the map from the bulge to the constriction, hence the differences in area in the exponent. The motivation for our work is that we found that the PLC prediction is much less than the complexity of standard tensor networks. Our goal was to try to find explicit tensor networks which have the same complexity the PLC predicts, to see if we can find evidence in support or against the PLC, better understand what properties are required for it to be correct, and understand if these properties naturally emerge in holographic settings. In prior work, we found that the PLC predicts a sub-extensive complexity, which seems surprising. This was shown in spatially extended Python's lunches with IR regulators. When the IR regulator is large enough, the index 1 surface can break the planar symmetry of the spacetime, leading to finite area differences between the bulge and the constriction, as shown here in the figure. Our goal was to see if we could verify this complexity prediction in an explicit tensor network model. To compute the complexity, we will represent the planar geometry with two mirror tensor networks glued together. We will explore the computational cost of contracting this map in two different ways. The first is to contract the mirror tensor network along the RG direction, which leads to an extensive computational cost. We can, however, contract the map sideways using chunks which only have non-vanishing mutual information with their neighbors. This Markovian or MPS approach leads to a sub-extensive computational cost, though one which still exceeds the PLC prediction. We trace the source of the greater computational cost to a property called computational covariance. The PLC prediction assumes that the map is simple in every direction, so no matter how the map is contracted, the only source of exponential complexity will be post-selection. Mera, however, is not computationally covariant. It is only simple along the RG direction. In this direction, though, the area differences are extensive. When we try to contract the map in a different direction via the MPS or Markovian approach, we find sub-extensive area differences at the cost of the map no longer being simple, so each chunk does not have a polynomial complexity. It instead has complexity exponential in its size. Having now traced the key property needed for the PLC prediction, we were then led to explore how common this property is in tensor networks. In particular, we asked if random tensor networks are computationally covariant. They seem like natural candidates since they do not have a preferred direction. Further, once a slice is chosen, random tensor networks will generically preserve inner products, which is necessary for information recovery. But they are not close in trace distance to any unitary, and the closest unitary to the random tensor network will generically have a complexity exponential in the Hilbert space size, so they are not computationally covariant. We then sought to define a tensor network which satisfies computational covariance, and therefore the PLC prediction. We call these tensor networks Twirled Perfect Tensor Networks. They begin with perfect tensors at the vertices, which are isometric as maps from any smaller subset of legs to any larger subset of legs. But perfect tensor networks generically are stabilizers, so they do not explore the full Hilbert space. We overcome this by contracting each leg of the perfect tensor with a random unitary, a process we call twirling. We can then reach generic states in the Hilbert space while preserving computational covariance. We then showed that twirled perfect tensor networks reproduce the RT formula in the large bond dimension limit via mapping to a statistical Ising model similar to the original random tensor network calculations. This allows us to relate areas to entropies and reproduce the PLC complexity prediction. In conclusion, we showed that the PLC prediction seems smaller than expected from standard tensor network results. We trace this to the PLC imposing an additional assumption of computational covariance. Random tensor networks we find are not computationally covariant, but we define a novel class of tensor networks called Twirled Perfect Tensor Networks, which are computationally covariant, generic, perfect, and recover the PLC prediction. Though Twirled Perfect Tensor Networks were motivated by holography, they may have broader applications and future work could explore their properties. Thank you.